Hello everyone, welcome to this presentation. My name is Helong. I'm from the University of New South Wales. Today I'm going to present to you a paper titled A Method for Covert Video Surveillance of a Car or a Pedestrian by an Autonomous Avion Wire Trajectory Planning. Today's presentation consists of the following parts: introduction, problem statement, proposed solution, simulation result, and conclusion. Now let's start from the introduction. Unmanned aerial vehicles, also called drones, have been widely used in civilian domains, such as wireless communication support, video surveillance, parcel delivery, monitoring, and target tracking. Thanks to advancements in cost reduction, mobility improvement, and many promising research results in the control of UAVs. The utility of a UAV for target tracking is a less inconspicuous and much more cost-effective option than the conventional surveillance carried out by police helicopters in terms of the size and the manufacturing and maintenance cost of the vehicles. For target tracking, UAV can be equipped with cameras, and it is often required that the mobile target is always within the effective range of the camera. In this application, trajectory planning is a fundamental problem which affects the video quality and tracking efficiency crucially. There are two typical scenarios that have been comprehensively investigated in the literature regarding target tracking by UAVs. The first one is that while a UAV monitors a target, the movement of the target is independent of the UAV. The other scenario is that a UAV attempts to monitor a target that is aware of the UAV and tries to avoid being monitored. In this paper, we consider a different scenario, which is called covert video surveillance. By this covert video surveillance, we mean that a UAV monitors a target, and the UAV needs to disguise its monitoring intention visually from the target. A potential application is that a police officer wants to monitor a criminal suspect, but it doesn't want the criminal suspect to know he is being monitored. Okay. In this case, when the police officer uses a UAV, the UAV needs to somehow disguise this intention. Two issues are addressed in this paper. The first one is how to characterize disguising, and then how to design an energy-efficient trajectory accounting the disguising performance. In terms of energy efficient, we mean that most UAVs are powered by the onboard battery, okay, and if it cannot harvest the energy from solar or some other means, the usable energy is limited. So improving the energy efficiency can elong the lifetime of the UAV. Problem statement. In this section, we will start from the basic UAV model and then formulate the problem. The UAV is modeled by this linear function. Here, xy is also denoted by this p to represent the position of the UAV. This is the linear speed, heading, and angular speed. The position of the target is q, and we assume that when the target is moving along a road, the position is predictable. The UAV is carries some cameras, okay, and it can see a certain area on the ground. Then, for a target, if the UAV wants to see it, it has to fly in a certain range, and this range is called the UAV flying area. So in this paper, we monitored by this circle sector, but it is not limited to this kind of area. It can be any other shapes, but it should depend on the type of the camera. When the prediction of the target position is inaccurate, okay, for example, it can be any position between these 2 points. then the UAV flying area becomes smaller, since it has to accommodate the uncertainty in the target position prediction. So in this case, we use this phi to represent the feasible flying area, and the position of the target at any time should be within this site. Next question we discuss is discussing how to mathematically characterize discussing is very important in this paper. So our idea is very basic. It's from some common sense. Suppose you are sitting on a bench. On your right hand side there is a person keeps watching you. If this person doesn't change his position, it's with a high probability of being detected. You will somehow notice, okay, that someone is watching you. So based on this idea, we propose to use the derivative of the UV target distance and angle to model the discussing performance. So here is the angle, here is the distance, and this is the derivative of them. This is used to model the disguising performance. The larger this is, the better the disguising is. Okay, and for energy efficiency, we used the length of the trajectory to indicate. And during this interval, we wish that the energy efficiency is, we use this one to model the energy efficiency. Okay, the larger this is, the worse the energy efficiency is. So we wish that the length of the trajectory is not that much. Okay, based on these two considerations, we formulate our overall objective function, which is a linear combination of disguising and the energy efficiency. We want to minimize the length and we want to maximize the disguising. Solution. We proposed dynamic programming based framework. So in terms of dynamic programming, we need to have a state space, and we need to have the state transfer cost. Okay, we will define them here. So the first thing is to discretize the mission duration of 0 to t into a certain number of slots. Next, we discretize the UV flying area at each slot into a number of points. Okay, these points constitute the state space. We use Sk to represent the state space of this phi, and we will see that it is also denoted by phi previously. The next step is to define the state transfer cost, and here from a state I in Sk to a state j in Sk plus 1, we use the notation Cijk to represent the state transfer cost from this state to this state. And we will discuss this detailedly sometime later. Okay, and the third step is to formulate the recursive equations, and it is given by this. So here we have an initial state is F, which is represented by S, and the final state is F. As we have the initial condition, so S is given, okay, but we do not have any requirement on the final state, so F is unknown. For the final cost, we define it as 0 because we do not have any restriction on it. So here, capital JKJ is the minimum cost from the initial state S to a state J. So our global minimum cost is given by Jn, okay, which is given here. Using this algorithm to find the Jn, and then apply a standard backtracking algorithm to recursively find the optimal path. That's it. This is the basic framework of dynamic programming. So here we need to address the issue of state transfer cost, Cijk. From this state to this state, there is an infinite number of passes. So here is an example. We have this state I, and we want to go to this state J. Okay, and here is the position pk. And here is pk plus 1. There are multiple feasible paths. For example, here, one path, here, another path, here, one more. Okay, there is an infinite number of passes. So what we do is to define a very simple but effective movement strategy. Okay, so at the beginning, the UAV applies the maximum angular velocity until it is heading towards this position. Then it moves to this position along a straight line. During this slot, we require that the UV moves with a constant linear speed. So we use this figure to represent it. At this pk, it has a certain heading CDK, okay, but we do not have any heading requirement on the next state. So here, the UAV needs to decide which direction to turn, left or right, and the criteria is that a shorter path should be found. So in this case, definitely turn right is better than turn left. Okay. Then when it decides the turning direction, it has to calculate the the linear speed, because the angular speed is set as the maximum. We try to find out some equations to characterize this arc and also this straight line. By solving this equation, we can find the linear speed. With this linear speed, we will be able to find out the turning radius. Okay, then the turning center can be found, and then we can find this tangent position, zk. So the UAV at this position with this heading will turn right along this circle, and when it meets zk, it will leave the circle and go to the next state. Okay, there are some equations that we need to construct to find out this v, and you can have a look at our paper to find more details. This is the proposed solution, and with it we can conduct some computer simulations, as you can see here. A target is moving along this road, and this is the UV's trajectory. We did the simulation with different parameter of lambda. If you can remember, this lambda represents the weighting factor in the cost function. Okay. The larger this lambda is, the more significant the UV moves. Yeah. Conclusion. So in this paper, we consider a problem of covered video surveillance. We proposed a metric for disguising, which is the combinations of the derivatives of the UV target distance and angle. We formulate an optimization problem for the path planning, and then a DP-based method is derived, which accounts the UV dynamic model. So using this method, the UAV can find we can find a trajectory for the UAV such that it can see the target at any time, and it can behave somehow like randomly to avoid being detected by the target. Okay, this is the end of the presentation. Thank you very much.